Have you ever wondered if a moving car, a running human, or a flying bird follow the exact same rules of science? Well, today, we're breaking down the fundamental physics concepts of motion. We're going to learn what motion actually is and explore distance, displacement, speed, velocity, and acceleration. Let's get right into it. Okay, let's dive right into this. Whether it's a sports car zooming down a highway, your friend sprinting across a field, or a bird soaring through the sky, literally every single one of these actions is governed by the exact same principles of motion. It doesn't matter if we're talking about everyday life on the ground or the skies above, physics applies universally to all movement. No exceptions.
Here's our roadmap for today's explainer. First, the basics of motion. 2. Distance versus displacement. 3. Speed and velocity. 4. Acceleration and motion graphs. And finally, motion in daily life.
Section 1. The basics of motion. Understanding movement.
So, what exactly is motion? Quite simply, when an object changes its position over time, we say it's in motion. Imagine a ball just sitting perfectly still on a table. Right now, it's at rest. But the moment you give it a little push and it starts changing its position over time, like, a rolling ball, it is officially in motion. It's all about that change in position as the clock ticks forward.
Now, motion isn't just one single thing. It mainly falls into 4 different categories. First, we have rectilinear motion, which is just a fancy way of saying movement in a straight line, like a train on a track. Then there's circular motion, like the rotating blades of a ceiling fan. Third is periodic motion, which follows a repeating path, like a swinging pendulum in a grandfather clock. And finally, random motion, which follows an irregular, unpredictable path. You can probably spot examples of these all around you every single day. Section 2. Distance versus displacement, mapping the path.
So, the crucial point here is understanding the fundamental difference between distance and displacement. They sound kind of similar, but in science they are very different. Distance is the total path covered by an object. It's a scalar quantity, meaning it only has a size or magnitude. Displacement, on the other hand, is the shortest straight line distance between the starting position and the end position. It's a vector quantity. This means displacement cares intensely about the direction you're going, while distance simply does not.
Let's ground this theory in practice with a simple mathematical example. Imagine you walk 10 meters forward, and then you turn right around and walk 5 meters backward. The total distance you walked is 15 meters, right? Because 10 plus 5 equals 15. That's the total physical effort you put in. But your displacement, that's just 5 meters, because from your original starting point, you only ended up 5 meters away. Distance is the whole journey. Displacement is just the absolute shortest shortcut from point A to point B.
Section 3. Speed and velocity. How fast and where? All right, first up is speed. Speed tells us exactly how fast an object is moving. The formula is beautifully simple. Speed equals distance divided by time. Just like distance, speed is a scalar quantity. It simply measures how fast a distance is covered without worrying at all about which way the object is actually going. And this brilliantly illustrates the math in action. If a car travels a distance of 100 kilometers on a highway and it takes exactly 2 hours to complete that journey, we just divide 100 by 2. This gives us a highly practical speed of 50 kilometers per hour. Pretty straightforward, right?
But what happens when we care about the destination? That is where velocity comes in. Let's compare them directly. While speed is distance divided by time and is a scalar, velocity is displacement divided by time, making it a vector. This basically means velocity is just speed, but with a specific, highly important direction attached to it.
Let's cement this vector concept. Suppose a person walks 20 meters perfectly east, and it takes them 4 seconds. We divide the 20 meters by 4 seconds to get 5 meters per second. But because it's velocity, we don't just say their speed is 5 meters per second. Their velocity is specifically 5 meters per second east. That directional tag is exactly what makes it velocity.
Section 4. Acceleration and motion graphs, changing speeds and visualizing data. We know how to measure steady movement, but what if that speed changes? When an object's velocity changes, we get acceleration. Acceleration is formally defined as the rate at which velocity changes over a given period of time. The formula? Acceleration equals the change in velocity divided by time. It's literally that push you feel in your seat when a car suddenly speeds up on the highway.
Let's walk through a quick bike example to make this super concrete. Imagine you're on a bike at a dead stop, so your initial speed is 0. You start moving, and 4 seconds later, your speed is 20 meters per second. Your change in velocity is 20. Divide that by the 4 seconds it took, and you get an acceleration rate of 5 meters per second squared. That means every single second, you are going 5 meters per second faster than the second before. How cool is that?
Now, this changing of speed leads us to two broad classifications of motion: uniform and non-uniform. Uniform motion means an object covers equal distances in equal amounts of time. Think of a train cruising smoothly at a perfectly constant speed. Non-uniform motion, however, means covering different distances in equal times. A perfect example is a car stuck in heavy traffic, speeding up, slowing down, stopping, and starting. Its rate is constantly changing.
Now, what's really interesting about this is how easily we can visualize all of this data. A distance time graph is the absolute fastest way to understand motion at a glance. If you plot the motion and get a perfectly straight line, you're looking at uniform motion. But if you see a curved line, that immediately tells you it's non-uniform. We can instantly determine an object's speed behavior just by looking at the shape of its line. It is a fantastic visual shortcut.
Section 5. Motion in daily life. Why it matters.
Why do we actually study this? Because the physical principles of motion literally run our world. These mathematical rules are what engineers use to power cars and airplanes safely. They're absolutely essential for understanding and improving human performance in sports. They are the exact calculations that allow us to launch rockets into orbit. Simply put, without the principles of motion we just mapped out, absolutely none of our modern transportation would function.
To sum it all up, today we learned what motion is, its types, distance, displacement, speed, velocity, and acceleration. We went from a simple ball rolling on a desk all the way to understanding the graphs of non-uniform acceleration. If you found this explainer helpful in breaking down these physics concepts, please make sure to like, share, and subscribe so we can keep bringing you clear, structured content. But before we wrap up completely, I want to leave you with one final, mind-bending thought. Think about everything we discussed regarding objects at rest versus objects in motion. Since the Earth itself is constantly rotating on its axis and orbiting the sun at incredible speeds, are you really at rest right now, even just sitting there in your chair? Think about that relative motion, keep questioning the world around you, and I'll see you in the next explainer.